For decades, Mars has been holding on to this secret, one that's hidden in its thin, cold atmosphere. Our very best scientific models just couldn't quite get it right, and that meant a fundamental piece of the planet's chemistry was missing. But now, thanks to a new eye in orbit, we've finally started to crack the Martian Code.
So to get started, just think about our own planet for a second. High up in our atmosphere, there's this crucial molecule that shields all of us from the sun's most harmful radiation. You've definitely heard of it. And as it turns out, it's also swirling through the skies of Mars. Any ideas what that might be?
That's right, it's ozone. But here's the thing. On Mars, this familiar molecule behaves in some very, very unfamiliar ways. And as scientists were about to find out, understanding its bizarre daily cycle was the key to unlocking a much bigger atmospheric puzzle. Okay, so here's the heart of the puzzle. For years, we knew ozone was on Mars, but our view of it was, well, incomplete. We could see the what, but we had no idea about the where or the how. And this wasn't just some small gap in our knowledge. It was a huge blind spot that was seriously holding back our understanding of the entire planet. Think of it like this. All the previous missions could only get what's called a column measurement. It's kind of like flying over a forest and just seeing the canopy from way up high. You know there are trees down there, sure, but you have no clue how dense the forest is or how the trees are layered at different heights. What we really needed was a vertical profile, a way to see every single tree to understand exactly how ozone was spread out at different altitudes. And this is why it was such a big deal. Our climate models for Mars, these are our best scientific predictions for how the planet's atmosphere should behave. They were just consistently wrong. For a scientist, that's a massive red flag. It tells you you're missing a fundamental piece of the puzzle. Something really crucial was happening that we just couldn't see. To get that high-resolution, tree-by-tree view, we needed a new tool, a new detective on the case. And that detective arrived in the form of the European Space Agency's ExoMars Trace Gas Orbiter, or TGO for short, which carries this incredibly sensitive instrument called NOMAD. So TGO uses this really clever technique called solar occultation. Twice every single orbit, right at sunrise and sunset, it positions itself perfectly to watch the sun through the very edge of the Martian atmosphere. As that sunlight filters through all those different layers, the chemicals in the air absorb specific colors of light, and that leaves behind a unique chemical fingerprint that the NOMAD instrument can read. Here's a great way to think about it. It's like watching a sunset through the steam rising from a kettle. The steam changes the light, right? It makes it look different. Well, by studying how that light changes, you can figure out exactly what's in the steam. NOMAD does the exact same thing, but its kettle is the entire atmosphere of Mars. Pretty cool, huh?
So, with this powerful new eye on Mars, what did we find? Well, scientists uncovered this secret chemical dance happening in the Martian sky, a surprisingly intimate relationship between ozone and, of all things, water vapor. Now, the scientific term for this relationship is anti-correlation. It's a simple but really powerful idea. When one thing goes up, another thing predictably goes down. They are totally linked, but they move in opposite directions.
It's basically a chemical seesaw. On Mars, wherever you find more water vapor, you find less ozone. And in places where the atmosphere is super dry, ozone can build up. We now know this happens because sunlight breaks down water molecules, and that creates these byproducts that are just incredibly effective at destroying ozone.
But wait, it gets even more interesting. This chemical seesaw isn't balanced the same way all year round. Nope, it tilts dramatically depending on the Martian season and where the planet is in its long oval-shaped orbit around the sun.
See, Mars has really extreme seasons. When it's at aphelion, that's its furthest point from the sun, the atmosphere gets extremely cold and dry. But then, as it swings around to perihelion, its closest point, things warm up and a lot more water vapor can get into the atmosphere. And this whole cycle can get supercharged by things like that massive global dust storm in 2018, which acted like a giant elevator, pushing huge amounts of water vapor to surprisingly high altitudes.
And this seasonal change has a direct impact on our chemical seesaw. During that cold, dry aphelion period, with way less water vapor around to destroy it, ozone levels build up to their peak. But then, during the warmer, wetter perihelion, that increase in atmospheric water vapor leads to widespread ozone destruction.
So the seasonal pattern was a huge piece of the puzzle for sure. But the real smoking gun, the one clue that truly cracked this case wide open, came from comparing the atmosphere at two very specific times of the Martian day: sunrise and sunset.
Remember, Nomad is always looking through the terminator, that line between day and night. So at sunrise, it's analyzing air that has just spent a long cold night in total darkness. But at sunset, it's looking at air that's been baked by harsh solar radiation all day long. And the difference between the two was just staggering.
How staggering? Let's just say this much: a factor of 10. Yeah. In a specific band of the middle atmosphere, Nomad found 10 times more ozone at dawn than it did at dusk. So what on Mars is going on? Well, during the long, cold Martian night, without sunlight to power those destructive chemical reactions, ozone just steadily builds up in the darkness. We see that peak right at sunrise, just before the sun's rays pop over the horizon and begin to erase it all over again.
So when you put all of these clues together, the detailed vertical profiles, the water ozone seesaw, those dramatic seasonal swings, and this daily boom and bust cycle, you finally start to see the complete picture of how the Martian atmosphere really works. And look, this is so much more than just solving an old puzzle. For the very first time, we have a detailed 3-day map of the ozone on another world. This data confirms just how critical the water cycle is to the planet's entire chemistry. And it gives scientists the missing piece they needed to finally fix those broken climate models. It's a genuine revolutionary leap forward in our quest to understand Mars. And all of this leaves us with one last, really important thought. We've just seen how a planet's protective ozone layer can be completely transformed by what seem like subtle shifts in water, temperature, and sunlight. So as we continue to study this delicate atmospheric dance on Mars, it really forces us to ask, what can this teach us about better understanding and ultimately protecting the fragile atmosphere of our own planet?